So for laser methods, there are three methods we're going to look at. And kind of all three of them use, well, the first two use very similar processes. The third one is still considered an optical laser testing method, but it's a little bit different. So these are, the first one is holography, and the second one is shearography. And those work in kind of similar manners. It's just the way the light travels is a little bit different. The last one is profilometry. And we'll look at that. That one works slightly different. It's a little bit almost simpler in design, but it's still a very accurate method. And these are becoming more common. We used profilometry for dent mapping on our airplanes, and it could do dent mapping of the skin, like when we have when a plane flew through hail or something like that. It sped that process up by orders of magnitude, where we have to manually map each dent before. That profilometry could map like an entire area all at once and send that data to the manufacturer to get approval to fly the plane after it got turned into a golf ball. But we'll start with holographic testing. So holographic testing is we use holographic technology to map a surface. And we have to do this. It's a comparison process where we're going to look at the surface at rest. We're going to stress the surface. We're going to stress the material. And then it's going to compare. Differences will appear based on how the material deforms when stress is applied. And so there's different ways we can stress the material. Some of the most common ones, mechanicals, things like bending or pushing on it. Heat, pressure. If you're dealing with an airplane, you can pressurize the pressure hull, for instance. Different vibrations or vacuum, and there's all kinds of ways of doing it. But the stress, ultimately what we're looking for is to cause some kind of a deformation. And that deformation, when you have changes in the structural condition, will alter how the deformation will alter the way the deformation takes place, will be altered by damage or changes to the structure. So the way this works is holography is we're looking at things called interference patterns in light. And you're all familiar with light being described as a wave. Many of you have probably heard of the duality of light, particle wave duality. So we're looking at light from the wave perspective right now. And a light wave, just like a sound wave, or just like a wave in the ocean, has a certain phase, right? And so what we do is we take light, and when there's constructive interference between two waves of light or two beams of light, you get an area that gets brighter, right? The wave, its amplitude increases. And when you have an area where the waves are out of phase, you get destructive interference, which looks darker when you view it. And so I've got some videos. If you can't remember how this works from physics, there's some videos there you can view, but I'm not going to pull them up today just for time's sake. But that kind of reviews kind of how light acts and lasers and that kind of thing. Now, normal photography, most of you are familiar with photography, we just look at light intensity in different frequencies, right? Different colors. How bright is it in the red frequency? How bright is it in the yellow frequency? How bright is it in the green frequency, right? How bright is it in blue? For holographic testing, we're looking at that intensity, but we're also looking at phase. And so our holographic cameras are able to detect the phase of light. And more importantly, they're able to detect whether light is in phase or not in phase with each other, okay, if there's more than one beam of light. So the way we do this is we start with a single laser beam. And when you have a laser beam, the key with a laser compared to ordinary light is that the direction it's going is aligned and the phase of all the light in the laser beam is aligned. So you start with a bunch of light that's all in the same phase, which is very bright, right? And we take that and we run it through a polarizing type filter, which splits the beam essentially into two beams that still have the same phase. Okay? So essentially we take half the light and we send half of it one way and half of it another way. And one of those beams we send directly over to our object. Okay, or sorry, directly over to our holographic plate, which is our sensor. Okay? The other beam we bounce off of an object, and when we bounced it off of an object, that first beam is called a reference beam. When we bounce that second beam off of our object, that is going to change, among other things, it's going to change the intensity and the phase, and most importantly for holographic testing, it's going to change the phase of that light hitting the object. So now when they come back together on our holographic plate, the light is no longer all in phase, right? The reference beam is in its original phase. The object beam, the phase has been changed after it hits the object. And so when they come together, our holographic plate is able to detect that phase change. And what you see is an image that looks like this. And so beams that are out of phase are going to result in the interference pattern. So the dark areas are areas where a beam is out of phase, and the light areas are the areas where the beams are still in phase. Okay? And so that's one picture. It records the interference pattern. Then we stress the object and project those same beams of light on it again. And as we stress the object, it's going to slightly change shape, right? If we pressurize something, it's going to get bigger. If we bend something, if we flex it, it's going to slightly change shape. And that's going to make our, we take then a holographic image of it under stress, and we can compare what it looks like not stressed to what it looks like stressed. And so we have a reference, we have to know what the object normally would look like when it's unstressed or when it's not damaged. So the people who develop this, they do a standard, right? They create, say we're doing the pressure vessel, the pressure hull of the aircraft. When you take a new aircraft that has no damage and they image it unstressed and they image it stressed and they look at what changes. And then when you go back and do a holographic test on a damaged structure, the way that hologram changes between unstressed and stressed is going to be different. And so now you can start to pick that up and take measurements and find areas of damage. Okay. The advantage of this is it's an extremely precise method, down to the 10,000th of an inch. Disadvantages, though, is it can cause potential material damage due to the stressing of the part, right? So then it goes from NDT to DT. We don't want to go into the DT realm, right? Now the plane becomes useless. It's very complex and requires special, expensive equipment. Everything has to be kept extremely stable. Movement and any of those, in the laser, the beams, the different mirrors, the object itself, any kind of movement is going to throw off that holographic image. And there can be, we've talked about diffusivity in thermography. Diffusivity can have an effect on it. So the big thing here I just want to point out is that in holographic image, we split our beams, and one of them goes directly to the plate. One of them, the reference beam, goes directly to the plate. The other one bounces off the object. But they are in phase until the point where the object beam actually bounces off the object, and that changes that phase. Okay? So that's the first of our 3 laser testing. The second one I talked about is shearography, so shearographic testing. And this is very, very similar to holographic testing, in that we are doing the same basic process. The part has to be mapped, and we take a shearographic image of the unstressed part, and then we take another one where it's loaded or stressed. And the stresses we use the same types of stresses that we used for holography. And again, the comparison is made between how it appears at rest and how it appears under stress. So you can see right now, it really doesn't look much different. Looks like a very similar method. And again, when there's a discontinuity, we'll be able to see it in how that surface deforms and how it deforms differently once it's been damaged compared to, or if it's not correct, right, compared to how it would deform as a known good part, or when it's undamaged. And so, but now we are using something called laser speckle pattern interferometry. So instead of looking at purely the phase, we're looking at a speckle pattern that results. And the setup for this now, you can see, is we don't split the beam before we look at it, okay? So we start with, again, a monochromatic, coherent, all the lights in phase laser. But now we project that laser directly on the part, and a rough surface, even if it appears smooth in the naked eye, remember, this is another method that can go down to that 10,000th of an inch. So it may be smooth to our eyes, it might even be smooth to touch, but it may be rough when you compare it to light, right? The scale of a light wave. And so the rough microstructure will change the phase of certain parts of that beam, okay? So we're no longer comparing a portion of the beam that's unaffected to a portion that's affected. We are basically gonna compare, there are areas where this beam is gonna bounce off the object, and it's gonna be smooth, or it's gonna be between rough points, and the phase is not gonna change, right? Certain areas it will reflect the light without changing the phase, but other areas will change the phase. And that's where that speckling starts to come in. So now when those pieces of the light beam, those different sections of the light beam interact, in some areas it's going to cause constructive interference, it's going to get brighter. In other areas it's going to cause that destructive interference. And that's what's going to cause this speckling pattern. And so the light then is picked up by a camera. It goes through what's called a shearing device, which is essentially a polarizing filter. And so you get those areas of varying intensity because of that constructive and destructive interference in different areas. And it creates a speckle pattern that we're able to pick up. And so this one, however, it's not something we can necessarily see with the naked eye. It's something that has to be processed. The image has to be processed pixel by pixel. And an algorithm is going to compare the intensity and the phase of the light at each individual pixel. Okay? And again, we are going to take our object unloaded and we're going to take it loaded. And as the part is stressed, we're going to compare how does this part, this maybe unknown part, or this part with suspected damage, how does the unloaded to loaded pictures compare, shear graphic pictures compare, to a part that's known good, right? One that's not damaged. And so then what you can do is start to place those, you can place those pictures over top of each other. The computer systems that do this essentially take those images or those pixels and they put them on top, or they compare them pixel by pixel, right? Pixels are a big grid. 1, 1, top left-hand corner. It compares it to 1, 1 on your known good image. Second pixel over in the top compared to the second pixel in your known good image, and third and fourth, and then the second row and the third row, right? To the thousands or millions of pixels that the computer's going to compare. And so essentially where the first one, where holography, we split the beam, and we looked at the interference between a beam that was unaffected versus a beam that's affected. Now we're looking at the unaffected portions of the beam compared to the affected portions of the beam that are all hitting the same surface. Okay. And this one has some similar advantages. Similar advantage in that precise measurement, 10,000th of an inch. It can do a relatively large area. And when I say large area, we're comparing to, something like ultrasound or something like eddy current, right? Where it's very small areas at a time. It's extremely fast, right? It doesn't take long to take a picture. Right? So that's essentially what it is. You have a laser hitting the surface, and you use essentially a camera to detect that, a specialized camera to detect the light coming off of there. Right? It takes 1 to 2 milliseconds for each picture. And then a computer processes it. And you can imagine a few thousand, few million pixels. Really doesn't take a computer that long to compare the numbers at all those pixels, right? A matter of seconds at the most. So disadvantages are very similar to holography. Possible material damage due to stressing the part. One thing that is different, because we are not using a reference beam, is that there has to be a certain amount of surface roughness. Basically, the surface can't be too smooth. If you have a surface that has roughness that's less than 1 wavelength of the light being used, you will not pick up any kind of a speckle pattern, because none of the light will change phase. So the roughness has to be more than the wavelength of the light. Now, remember, light's a very small, right, pretty small wavelength. It's complex and needs computer interpretation and equipment. And now this one is very sensitive to lighting conditions, because if you get extraneous light bouncing off that same surface that the camera picks up, that's obviously going to be a different phase. The light coming off of the lights in the room here is not in phase with it. It's all kinds of different phases, right? The light beams, the light waves are in all different phases right now. And so if that were to mix with the known good light that we have, it'll mess up our image. So we got to be careful of what kind of extraneous light is in the environment. Our third method is probably the easiest one, I think personally, is the easiest one to understand, because it doesn't involve all this like phase shifting. Right? When people start looking at phases of light, and it's not something we can see. We just have to kind of talk about the theory behind it. So profilometry, the root word in it is profile. And now we're going to use light to take a surface profile. We're going to create a 3D optical surface, essentially map or profile of whatever it is that we're looking at. So in this case, a part is scanned. It's used using optical methods. And again, it's a laser and camera or sensor array. And we produce something that's very similar to a topographical map. If you've seen a topographical map, that shows elevations, right? Where does the land get higher? Where are the low areas? And so we can essentially we use a camera to create a topographical map. This one also is very handy in that we do not need to stress the part. It is purely a mapping process. This is the one I was talking about. When we had planes fly through hail, we use this. We were able to put profilometry equipment up and essentially take pictures of the areas of the skin, and it would create a 3D map that we could then send with measurements, with numerical values for areas, depths, shapes of all these different dents. And we could then send that to the aircraft manufacturer to get engineering approval or to get a repair drawn up. So scan can be even a point, a line, or an area. And we're looking at things like morphology, the shapes, different step heights, and even things like surface roughness. And so what's happening here is reflected light is going to be measured and essentially just converted to a distance from the center. And it's doing that based on the intensity and the location. And the location is sensed based on time, right? We know light travels at a certain speed, right? It's not instant. There is a certain amount of time it takes for light to get from point A to point B to point C. In this case, point A is our light source, our laser. Point B is the surface of the object we're imaging. And point C is the camera or the sensing device that is picking up that light. So here's the basic setup is we have a laser and we have an image sensor. And so the laser and the image sensor are tied to one another. And essentially, the equipment running these two devices that's connecting all this is able to say, okay, the light flashed or turned on at this point, and it took this many microseconds to get from the laser to the lens or the imaging device. So that can give us a distance, right? So in the case of this one here on the left, the beam of light, that's hitting the top of this little triangle thing is going to get to the image sensor faster than the beam of light that's going to go down to the lower surface and back up. The other thing it's looking at is the intensity of the light, right? So the light that's coming down and hitting the right side of this little triangle, most of that is going to reflect off to the right, away from the sensor. So that area is going to appear dark. Whereas the light coming down and to the left of this little triangle section is going to bounce, most of it's going to bounce directly to the sensor, and so it's going to appear lighter. And so by comparing those two things, the time and the intensity of the light that's ultimately reaching the image sensor, as well as the location it's hitting, you can see you're hitting different locations, it's going to reflect into different locations. We're able to create a three-dimensional map of the surface of our part. So it's fast, we can do a large area. Again, it can get down to the 10,000th of an inch, and there's no contact or stressing of the part. The disadvantage is if we have translucent or reflective surfaces, that can make it hard to image, right? You've all seen the glare. Basically, if there is glare, or if you can see through it, it's difficult to image. It's very sensitive to movement in the environment. We're measuring something to the 10,000th of an inch, using basically the time it takes for light to move. Just moving the camera, if the camera is bouncing around or the laser is bouncing around, it's probably moving more than a 10,000th of an inch. And so that can throw that off, or the object. The surface must also be clean, because it's going to pick up any dust, dirt, or anything else that's on there. Or it could prevent the light from reflecting. So probably in aviation, what you'll see, this is the method you'll see most often. We had a profilometry camera at our bigger maintenance bases where we could do this kind of dent mapping. And that's the main thing we used it for when we had a big hail event or something like that.